Hi students, we are looking at the engineering mathematics 1, okay, for diploma first semester students of Tamilnadu, okay. This is where we stopped in the last class, characteristic equation of a matrix, right? Consider the linear transformation y equal to x. In general, this transformation transforms a column vector into another column vector, because this is a column vector and this is a square matrix, n by n square matrix, and let's say this is having n by 1. Then the resultant multiplication, that means after the multiplication, the result y would be a n by 1 column matrix, right? N by 1 cross n by n cross n by 1 will give you n by 1, okay. So y1 y2 and so on yn. By means of the square matrix A, where A equal to this, if a vector x is transformed into a scalar multiple of the same vector, that is x is transformed into lambda into x, then y equal to lambda x, right? So equal to a into x. So if you take x into common, ax minus lambda, this can be also written as lambda into I into x, okay, where I is the unit matrix of order n. We want to take x out of the that means we want to take x common. That is the reason why we introduced I here, otherwise it is not necessary. So a minus lambda I into x equal to 0, then the system of equations will have a non-trivial solution if this is equal to 0. That is delta a minus delta I, sorry, not delta, determinant of z of a minus delta I equal to 0. This is called characteristic equation of a, okay. Let's find the characteristic equation of a. What you need to how we can find? First, write lambda I, okay. This is a matrix, lambda I is 2 by 2, so lambda 0 0 lambda. Now a minus lambda I will give you 1 minus lambda 2 minus 1 4 minus lambda, okay. And equate the determinant to 0, that is 1 minus lambda into 4 minus lambda plus 2 equal to 0, nothing but lambda square minus 5 lambda plus 6 equal to 0. So you will get two roots out of this, okay. Those values are called eigen values, okay. Anyway, we will be looking at eigen values also in this topic, okay. Find the characteristic equation. Now you have to take I as 3 by 3, because this is 3 by 3, right? Okay, 1 minus lambda whole cube equal to 0, or this lambda equal to 1 is a triple root. We need to find the characteristic equation for all these matrices, right? Right. Let me do it for the first one, 2 by 2 case. What is a minus lambda I? A minus lambda I. This is not t, record it as lambda. A is 1 1 3 minus 1, okay. Right. Now you have to put a minus sign here. Somewhere here, okay. So I is nothing but 1 0 0 1, right? So this is lambda times I, right? So put lambda somewhere here. Okay, so nothing but 1 minus lambda 1 3 minus 1 minus lambda. Okay, now we need to find the determinant of it, that is a minus lambda I 1 minus lambda square minus 3 lambda. No, not 3 lambda, 3 only. Okay, so equal to characteristic equation. Okay, lambda square minus 2 lambda minus 2 lambda plus 1 minus 3, that is minus 2. So this is the characteristic equation for the first one. You can similarly find it out for all the 2 by 2 matrices. Let's do it for one 3 by 3 example. Perhaps this one. Sixth one. Okay, where all the principal diagonal elements are 0, right? Right. So a equal to 0 1 1 1 0 1 1 1 0. Okay, right, that is a 0 1 1 1 0 1 1 1 0. What you need to find is characteristic equation. How to find characteristic equation? Method is same, a minus lambda I equal to 0. First find what is a minus lambda I. A minus lambda I. Okay, minus okay, okay, lambda I, that means this is lambda, this one is 0, this one is 0, next one is lambda, next is 0, Okay, so nothing but okay, nothing but minus lambda 1 1 1 minus lambda, sorry, minus lambda 1 1 1 minus lambda. Okay, so this is what a minus lambda I is. Okay, just the main diagonal, since all the elements are zeros, they will be replaced with minus lambda here. Okay, as it is shown here, right? Okay, this is 1 1 minus lambda. Fair enough, fair enough. Right. Okay, let's find the determinant a minus lambda I and equate it to 0. That is how you will get the characteristic equation, right? A minus lambda into I e determinant and making it equal to 0, right? So let's find the determinant first. Determinant of this matrix A minus lambda I, A minus lambda I, right? Let's proceed from this row. The first one is minus lambda minus lambda into, delete this row, this column, lambda square minus 1 lambda square minus 1 minus 1 into 1 into this row, this column, minus lambda minus 1, right? Minus lambda minus 1 plus 1 in, sorry, plus 1 into this row, this column, 1 plus lambda. Yes, that is correct. Okay, let's now solve this. Lambda into lambda square is lambda cube minus lambda cube plus lambda plus lambda plus 1 plus 1 plus lambda. Okay, oh, nothing but minus lambda cube plus 3 lambda. Okay, 3 lambda, lambda plus lambda plus lambda, 3 lambda definitely, right? Plus 2 plus 2. Okay, let's equate this to 0. Nothing but you can you can sub you can multiply it with the negative sign, then this becomes lambda cube minus 3 lambda minus 2 equal to 0. So this is the required characteristic equation of the given matrix. Okay, right. Which matrix we consider? Yes, this one. Okay. So rest of the things are similar, so I'm leaving that to you. Okay. In this case, especially this is upper triangular matrix. Okay. I I think the characteristic equation nothing but lambda minus 1 into lambda minus, that is 1 minus a minus lambda I. So 1 minus lambda into 4 minus lambda into 1 minus lambda equal to 0. That is what the characteristic equation is, or otherwise lambda minus 1 into lambda minus 4 into lambda minus 1. Okay, if you just multiply all these three, you will get the characteristic equation. Okay, because it is a lower triangular matrix. Anyhow, if you proceed in this way also with the column by taking a column into consideration, you will get the same result. Okay, and it is the easiest way of computing determinant of a square matrix. Okay, by taking a row or column where the highest number of zeros are present. Okay, let's now discuss about eigenvalues and eigenvectors of a real matrix. What are these eigenvalues or characteristic roots? Let A equal to Aij be a square matrix of order n. The characteristic equation A is that of A minus lambda equal to 0. This thing up to here you already knew. The roots of this equation are called characteristic roots of the matrix A. The characteristics roots are also called as eigenvalues. What is eigenvector or characteristic vector then? Let A be the square matrix of order n. Let X be any non-zero column vector x1 to xn. Then this equation Ax equal to lambda x as a non-zero solution of x corresponding to each value of lambda. Okay, non-zero solution of x corresponding to each value of lambda is called eigenvector or characteristic vector or latent vector of A. Okay, so if you find any vector x such that which satisfy this equation Ax equal to lambda x, then that vector is called eigenvector. Okay, for any particular value of characteristic root or the eigenvalue. Let's first find the eigenvalues of this A, V, H, G, 0, V, O, 0, 0, C. Like I said earlier, this is what lower upper triangle matrix. So the eigenvalues are A, B, C respectively. That is what you will get at the end of the day. See here, lambda equal to A, comma B, comma C. Okay. Why like that? Because it is upper triangular matrix. If you proceed with this column, this is what you will get, right? Need to find only one minor in this case, A minus lambda into this minus this. Luckily these two elements are zeros, right? Even if this element is not zeros, till this one becomes 0. That is the reason why you will get lambda equal to A comma B comma C. Find the eigenvalues for eigenvectors of the matrix. Find the eigenvalues of eigenvectors. No. Find the eigenvalues and the eigenvectors of the matrix. This. How to proceed? Again, A minus lambda I. First find the characteristic equation. Then solve that equation. You will get the eigenvalues like this, right? For every lambda, you will get a specific vector called as which satisfies Ax equal to lambda x. That x vector is known as eigenvector as we discussed earlier, right? So eigenvectors are computed in this way. You just substitute um, in the a minus lambda I, you just replace lambda with minus 2 since we are finding eigenvectors for the eigenvalue minus 2. So this becomes 4 minus 2 minus 2 1 3 1 1 3 plus 2 1. Okay, so a minus lambda I This is not determinant. Here we are not finding determinant. Okay. A minus ax equal to lambda x. See equation. uh, this side, if you send this side to here and common the right side vector x, if you take common a minus lambda I into x, right? So this is a minus lambda I. uh, Now we need to understand the basis to find the eigen vector, right? What is the basis? You take the matrix as it is, 4 minus 2 2, right? Then 1 3 1, right? And then 1 3 1. Okay, I need to take augmented matrix if I have to speak strictly, but next time onwards I need not to take augmented matrix. That I will prove it now. Why? Because this B matrix is 0. Okay, whatever the elementary operations I will be performing on the A matrix, that have to be that are equally applicable to both matrices, that is B as well as A. But why are we not considering B? Because the thing is that right, the thing is that in case of B, it is entirely 0, right? That is the reason why we are not considering a B matrix particularly. Okay, let me clear that in a moment. That I wish I will make it clear. mm, I need to extend this, right? Okay. Okay, I'm going to perform the elementary row operations on this augmented matrix. Okay, or as we rightly remember, R3 equal to R3 minus R2. Now what I essentially do is I will convert this into row echelon form, that is upper triangular matrix. Okay, uh, R3 equal to R3 minus R2, and I'm writing the next operation also, R2 equal to, yes, R2 equal to mm, R2 R2 um, no, I will keep it. I'm not going to have this one right now straight away, right? Oh, right. So this becomes 0. Yes, 0 0 0. Now I will interchange the rows R2 and R1. Interchange symbol is what? R2 R1. What is the symbol for interchange? Okay, one line with double-ended arrow. Yes. Okay. Fine. I'm interchanging the two rows. Okay. After that also I'm writing the step here only. Okay, because of the space constraint. 1 3 1 here. 4 minus 2 2. So otherwise I'm going to move this to the top. This makes sense, right? Okay, fair enough. Now I'm performing my operation, row operation on R2 here. R2 must be equal to R2 minus 4R1. That is what makes the first element of the second row to 0. Where is that symbol? Right. So this becomes 0. What about this? Minus 2, minus 12, minus 14. What about the last element? 2 minus 4 minus 6. Right, that is correct. That is correct. Oh, this one is 0. Yes, this is 0. This is minus 14. Minus 2 minus 12 minus 14. 2 minus 4 minus 2. So minus 2. Okay. Okay, I need to do it cautiously. Otherwise, what it is taking too much of time. Okay, fair enough. Fair enough. Keep this here. Keeping this here. Okay. So this is your row echelon form. See, this is minus 14. Uh, just multiply with what negative sign. Okay. 14 14x2 plus 2x3 2x3 equal to 0. Okay. That is one equation. The other equation, see, that is the reason why I told you this column essentially is not required because all are zeros, right? Whatever the elementary operations you perform on the row, those elements are going to be 0 anyway. So you need not to consider that row, even though you are keeping that in mind that you are taking an augmented matrix rather than the matrix itself. Okay. Okay, these two are the equations. Now you have only two equations out of the three unknowns, so you need to assume one particular value uh, for what, for one reading. Okay, so divide this whole equation. One reading means one value of x, either x1 x2 or x3. Okay, divide all the equation with 7x2 plus x3 equal to 0. Right. Right. So x2 is minus x3 by 7. Right? Or otherwise x2 upon x3 is what? x2 upon x3 minus 7. Okay. So if you take x2 value to be minus 1, x3 is 7. Okay, that is what is happened here. Now if you substitute this minus 1 7 in this equation, you will get x1 to be minus 4. I am telling you again, I am reminding you, you need not to keep x2 to be minus 1. You need not to force x2 to be minus 1. That is one eigenvector. Okay, but there are many more vectors that are possible. Even if you negate it, still it will be the eigenvector for the corresponding eigenvalue. Okay, you can take x2 to be 7 also. Okay, there is no problem. Okay, I'm just explaining why you got this these particular values, how you got those particular values. Okay, now x1 is minus 3, x2 plus minus x3, x3 is 7, so keep 7 here or minus 3 here, 4, so x1 will becomes minus 4. Okay, so this is what you have to done, you have to do. Coming to the eigenvector for the lambda 2. Okay, this is the situation. Okay, in this situation also you need to do the same thing. Okay, or the similar thing. What you have to do, uh, keep it here. I'm not considering again these zeros. Okay, anyway they are not going to add anything except taking some space here. Okay, you got my point, I hope so. Right, fair enough. So the values you can see here, this is 0, minus 2 2, this is 1, this is minus 1. Fair enough. Last one is 1 1 3, minus 3. Okay, so what is the situation here? We need to perform the elementary row operations, right? If you want to perform the elementary row operations, this pivot element, this is called pivot element or principal element, it shouldn't be 0, right? Then move, interchange r2 and r1. Okay, the famous thing we did the last time. Okay, this is what we did the last time, right? Whenever you see any pivot element to 0, better to interchange. Okay, okay, after interchanging, what will happen? This becomes 1, this becomes minus 1, this becomes 1, this is 2, this becomes minus 2, this becomes 0, right? So you need not to perform the elementary row operations on what? On this, right? On the second row. Why? Because the element which you want to make 0 is already 0. Okay, now perform the elementary row operation on row 3, that is r3. r3 equal to r3 minus r1. That makes the first element of the third row, that forces the first element of the third row to 0. That is what is desired or required, whatever you may call it as. 3 minus 3 is 0, 1 minus 1 is 0, 3 plus 1 is 4, minus 3 minus 1 is minus 4. Fair enough. See these two, they are just the same. Okay, again what you can do is make this entire row to be 0. Okay, anyway that is a futile job, since we figured out these two rows are similar. We are we will end up with the two equations only as usual. What are those two equations? X1 minus x2 plus x3 equal to 0. That is one equation. What about the second equation? The second equation, minus 2x2 plus 2x3 or x2 equal to x3. Okay, right. Now substitute x2 equal to x3, x1 becomes 0. Now if you take 1 for x2, 1 for x3, if you take 1 for x2, x3 becomes 1, x1 becomes 0. So 0, 1, 1 is the eigenvector. Okay. Like I said earlier, you need not to take 1. Again, you can take minus 1, 4, 5, 6. Whatever the value you take for x2, x3 will get the same value. x1, it forces x1 to be 0. Okay. That's it guys. Eigenvectors is not very difficult to find, but you need to do all these required stuff. Eigen what is called row, converting it into row echelon form and finding the um, equations. Okay, and from that reducing the values of x1 and x2, x3. Okay, right. What is this? Define eigenvalues of a matrix. The definition is already there on the top. Define eigenvectors, that is also there. If two eigenvalues are equal, then the eigenvectors are linearly dependent. The characteristic roots of a real symmetric matrix are characteristics roots of real symmetric matrix are they will be real. Find the eigenvectors of this problem. This is not a difficult problem, right? Eigenvalues are 1 and 3. Hmm? Clearly, if you want to find the eigen vector for let's say eigenvalue 1, how to find? Again, we will go by this method. uh, Lambda minus, I'm just doing it in a hurry, 2 0 3 minus lambda. Oh, what is lambda here? Anyway, lambda is 1, so this becomes 0. So 3 minus lambda is 2. Wait a minute, this is 2 into the vector x1 x2. What is this vector? Column vector. X1 x2 equal to what? Equal to 0. What happened? Okay. Oh, okay. Equal to 0. Okay, fair enough. 2x1 plus 2x2 or x1 plus x2 equal to, see the final equation what you got here is x1 plus x2 equal to 0. Okay, yes, you need to find the eigenvector to satisfy this equation. If you take what you want to take, either x1 to 1 or x2 to 1. If you take x1 1, x2 becomes minus 1. 1 minus 1 is also eigenvector, or minus 1 1 is also a eigenvector. Okay, this is eigenvector, this is one of the eigenvectors. Okay, right. We will discuss from problem 6 from here. Okay, in the next session. Why? Because this session is going to be very lengthy, right? I'm going to stop it here. Okay, we'll be discussing all these consistency and inconsistency things in the next session. Okay, நன்றி வணக்கம். See how beautiful this nature is. You also start planting the trees. Let us bring a new change in our society. Let us plant the trees and let others plant the trees. Let's take this pledge seriously from now. Thank you.